Hello. The purpose of this video is to show you someone else's channel. This is called One on Epsilon, and this is a channel in which my friend Yoni talks about programming in Julia, and he's got some of his own lectures in data science on this channel. So I had the opportunity to contribute to his channel through my teaching with the University of Queensland in a Masters of Data Science course. So what I'm doing in this episode of, let's call this another Mathematica Sessions video, what I've done is simply cut one of the videos that appears on Yoni's channel that I did with Yoni and trimmed it down so that it's only, say, a 45-minute video. But it covers Mathematica and Julia language programming to do a problem set in Yoni's course. So if that's what you're interested in today, then keep watching and give Yoni's channel a subscribe and check out some of his videos. I'll see you.
Anaconda. Okay, now the second thing I want to open up, I'll just keep it in the background. I've got a PDF file. Now basically, well, I'm not great at using Julia, basically, because I don't know all of the syntax perfectly. All right, so in order to understand what I'm seeing, what I usually do is I'll type up some code in Mathematica. Now that was part of the 7501 course that some of you did. Okay, so for some of you that might be familiar, but what I have is some comments, because I've commented what's going on in each of the problems. So I'll possibly need to refer to that from time to time. Okay, but that's here. And so I'll make it a little. So our first problem would ask us to construct a 3x3 matrix A, then to take the trace, the determinant, and the inverse. Okay, so if you don't know what the trace of a matrix is, it's simply the sum of the diagonal elements. Okay, all right, so now how would you do that in Mathematica? Well, I would write this, the 3x3 matrix, something like this. Okay, so we'll take this matrix as an example. So you can see that the syntax is different and that it has curly brackets. But what you want to know is how to do that in Julia. Okay, so below that, I've got the code for Julia, how you input the very same 3x3 matrix in Julia. And now we put a square bracket to start with, and then we space out our entries using the space bar. And when we want a new row, we put a semicolon in to indicate that we want a new row. Okay, so let's go over here to the Jupyter Notebook. So in Mathematica, you can save as PDF. So that's what I've done. You don't have to have Mathematica installed on your system in order to open a PDF, which is handy, right? Okay, anyway, back to this. So the first thing we need is to write using linear algebra, okay? And then Shift Enter to make sure that that will work for us. Okay, and it usually takes a little bit of time for these preliminary things to be loaded. Okay, so if that's gone through, then I'll just press Shift Enter in the second cell to input this matrix. Okay, so we see the asterisk was there for a moment, and now that's gone into memory. Okay, so you can see that that works. Now you want to try this out yourself on your own system and see that you can do this. All right, next, the trace. So as I said earlier, the trace is simply the sum of the diagonal elements of the matrix. So we can see that that would be 1 plus 1 plus 1. Okay, which we know is 3. So let's try this. Trace of A is 3. And let's just notice the syntax here. That's a lowercase tr and a round bracket. And we just put the A in because that's in memory above. And we've got the trace. Okay, the next thing that we want to do is calculate the determinant. So det of A. Now, sometimes it's handy to do this sort of thing by hand as well, so that you can see that your computer calculations agree with what you've got by hand. All right, so here we get 104 for the determinant of the matrix, and that looks plausible. Okay, so the next thing we're going to consider is a formula for calculating the determinant of a 3 by 3 matrix, and you probably would have learned this early on in your mathematical studies, like maybe a first-year university, or for some of you, high school. And so what that looks like is you would calculate the determinant of a 3 by 3 matrix by taking the element in the top left corner. In other words, the first row and the first column. Okay, so what we're talking about now is how do you do indexing, and how do I use indexing to calculate the determinant of a matrix? So that's the next part of this exercise, because indexing in any kind of computer software, well, let's say specific to mathematics or just computer science, indexing is a fairly important thing to be able to do. You want to be able to pull out specific elements of an array or a list or a string or something like that. Okay, so here the A subscript 1, 1 element, first row, first column, is A square bracket 1, comma 1. Now, if I were to do this in Mathematica, I would put A and then 2 square brackets and then 1, comma 1, and then I'd end with 2 square brackets. Okay, so that's the A11 entry. And then remember, if you're using the formula to calculate the determinant, that involves some minors, which are determinants of some elements or smaller matrices, 2 by 2 matrices within the larger one. Now, if I just take the mouse, because I know that all of you should be able to see my mouse cursor. Is that right, Walla? Can you see my mouse cursor on Zoom? Yeah, good. Okay, so I'll highlight this. It's this one times the determinant of this section, where you ignore the 7 there. I'm trying to highlight the 1681, right? So the determinant of that 2 by 2 matrix times 1 would be an important part of this calculation. All right, so the question is, how do I do that? All right, so we need a determinant of a 2 by 2 matrix. All right, so that we have below det A, and then what we have here is 2 colon 3. All right, now what that should be taking, if I remember right, is the second to the third rows of the matrix A. And then the comma tells us that we're taking the second to the third column within that. Okay, so that does give us this 2 by 2 matrix containing 1681, but we're applying the determinant to it. And remember, this is a scalar multiplication here, so we have just a star there. Okay, the next part is we subtract what is in the first row and the second column. So that's -2, right? And so A12, and then we're multiplying by another determinant. Okay, so this one is slightly different. So you'll see inside there, we've got A square bracket 2 colon 3. So that's this second to the third rows. But then we see something new here, square bracket 1, 3. So Julia has this nice way of saying I select the first and the third column out of the second and the third rows. Okay, now I did this in Mathematica, but it wasn't as easy to enter, let's just say that. Okay, so Julia's got some nice features in the syntax that are a little bit simpler in some ways, but every software's got pros and cons, right? So later we'll see how symbolic calculation is handy, whereas Julia doesn't do symbolic calculations. Okay, but a lot of the syntax is quite nice. All right, now continuing on, we then multiply by the A subscript 1, 3 entry, so top row, third column, and then multiply by the determinant that we get by crossing out the row and the column that entry is in. In other words, so if I'm crossing out the 1, 2, 3 and crossing out the column that contains 3, 6, 1, then I'm left with 4, 1, 7, 8. And that's the determinant that I want in that formula, okay? Fortunately, that's fairly simple here in Julia because we just have det a square bracket 2 colon 3 for the second and third rows. And then we want the first and second column within that. And that gives us the matrix 4, 1, 7, 8. That I've got a symbolic calculation of the inverse of the matrix A. Now that should be the same inverse, all right? But what you see are rational numbers, represented as rational numbers in that inverse. And we can see that some of those have a denominator of 104, whereas that would have been simplified in other entries. Okay, so that's what Mathematica does. Now, in Julia, I understand, since it's not doing anything symbolic, it will want to take entries that are decimal numbers and then form an inverse from those decimal numbers. Now, those decimal numbers are approximations of well, they would be just treated as rational numbers, right? Because they're real numbers that have been truncated in the calculation of the entries of that in Julia. And so when you take an inverse, you don't get precisely the exact inverse. You get a close approximation because it's done with truncated numbers. So what we have here in the display for Mathematica is the recipe for those numbers, right? Whereas a decimal approximation is just an approximation of these numbers, for example. Okay, so let's have a look at our problem. What we wanted to do was take the inverse of the matrix A and then I think multiply the inverse by the original matrix and see how that was. Okay, so I've done that in Mathematica in two ways, numerically and precisely. So let's have a look at this in Julia now. So we'll enter AI. So AI is just what we're going to call the inverse, okay? So we're putting this in memory. And that's running, takes a little bit of time. Okay, so, and now we'll go and take the inverse of the inverse. And you can see that what we now have, even though we input integers, we can see that these are integers. They just have 0.0 after them. So they're floating point numbers in here, but you can see it's accurate, okay? All right, so moving on. Okay, so this one is somewhat of a theoretical exercise at first. So I'll just verbally talk you through that. Okay, so it says, consider this matrix equation. We've got a matrix C times a vector X, or a column matrix X. And then we add the transpose of X transpose D, and that's equal to X plus B, where those C, D, and B are given having two rows. Okay, and now what we're aiming to do is solve this equation for X. Okay, but we'll want to do a little bit of a theoretical calculation first, so that we can enter this in the computer more easily. Okay, so the first thing you can notice is that the transpose of the product AB is B transpose A transpose. So we can apply that to this first. So if we transpose X transpose times D, then what we have is D transpose times X. Okay, so that's our first step. And then next, since we want to solve for X, we would like to take X to the same side of the equation and collect if possible. So we'll then subtract X from both sides. But notice that X is I times X, as in the identity matrix times X. And that's great because that gives us an opportunity to factorize out the X and place it on the right of all of that, because now it's common on the right-hand side of each of those three terms. So we can factor that out and put it on the right-hand side, and inside the bracket on the left, we have C minus D transpose minus the identity matrix, and we're solving this equals B times X equals B. Okay, so that's great. So that suggests to us all we have to put in memory in Julia is, well, we might want to call A, as we have here, C plus D transpose minus I. Okay, so let's try this. Error D not defined. Okay, that's because I skipped this, so I'll have to go up here and include that calculation. So that should be in memory now, and now we'll scroll down and run this, and we'll put A in memory as C plus D transpose. Again, you've probably seen this before, but the dash, that's meaning transpose. Okay, that's Julia's syntax for transposing a matrix. Okay, great. And we see that we in fact have a 2 by 2 matrix A that's been returned. And so that tells you that somehow Julia knows what I is, right? Even though it could be a 3 by 3 matrix, for example, right? So it seems to have taken that from context, but I'm only guessing because we're adding 2 other 2 by 2 matrices. So that's rather clever. Okay, but it probably relies on having used this linear algebra package that we set up at the start. Okay, next we want to solve for x. Now, this is a lot like the syntax in MATLAB for solving a linear system, right? Whereas in Mathematica, to do the very same thing, I would write linear solve. Okay, so this is a bit more like MATLAB, the syntax. So x solution, A backslash B. Okay, so let's try that out. And it returns a solution. So great, you're still there. Okay, great. So next, there's some calculations on checking this. So let's just try this. Checking. So this is, I believe, the top expression up here that we're just going to run. Okay, 1.25, 2.3125, great. And now does that match the right-hand side? Yes, excellent, it matches. Okay, great. Now, I'm going to have to peek at my notes here because just staring at what says in 30, I don't immediately know what we're meant to do. So let's have a look. Okay, I think that's at the top of this page. Okay, so it says build a 5 by 1 matrix U of ones. Okay, and I've got the code here in Mathematica to do that, which would be constant array, and I would place the 1 in there, and I would tell the dimensions. Okay, the next thing we would want to do is build a 5 by 1 matrix V consisting of integers 1 to 5. Okay, so the numbers 1 through 5 is the matrix V. All right, and then what I want to do is take their dot product in 2 different ways. So remember that the dot product of 2 vectors is defined to be just multiplying their rows together and adding the result. So it's a sum of the product of all the rows together, all right? But the key is that you can do this conveniently with a matrix product if you just first transpose the one on the left and multiply them as matrices. And that gives you the same thing, the dot product. So in Mathematica, I've got to get rid of some extra brackets because when I do it with matrices, I get some extra brackets when I was hoping to get a scalar number. So I've got to get rid of those. So I think in Julia, that's unnecessary. So let's have a look. Okay, so the first one is fill. We've got a round bracket 1, 5. So this is giving us a vector with 5 entries, but all of the entries are equal to 1. Okay, now the next is what would be table in Mathematica. So that's just 1:5. And that gives me 1, 2, 3, 4, 5 in a vector. Okay, and then here you can see that we have the calculation of the dot product in 2 ways. So on the left, just dot U comma V, and on the right, U transpose times V. And now I see that the asterisk takes care of matrix multiplication, whereas in, say, MATLAB or Mathematica, you would need to use different syntax. and different in each one, okay? Okay, now, and second thing I want to note is that we don't need to put a round bracket on either side of this. So just putting the one thing, comma, the next thing, and then calculating that, that gives us this 2 tuple below. All right, so let's try that, and we do get 15, comma, 15. Okay, so 1 plus 2 plus 3 plus 4 plus 5. That's a triangle number, and that adds up to 15. A equals reshape, collect. All right, so we want to know what this is asking us to do, because if you're not familiar with Julia, you just see these commands and you wonder, hey, what's the question? So let's have a look at my PDF here. Okay, so my notes say that we make a list of the integers from 1 to 21. All right, now the prime factorization of 21 is 3 times 7. So then we should be able to form out of that a 3 by 7 matrix. Okay, so that's the next step. From that, form a 3 by 7 matrix in which we count from top to bottom. Okay, now that's exactly what I've got here displayed. All right, you see 1, 2, 3 goes top to bottom here. So that's what we're aiming to do in this. So that's what this command does. So on the inside, we've got 1 to 7, precisely what that's doing. But once we form this list of integers from 1 to 21, we reshape it to be a 3 by 7 matrix. Okay, so maybe that syntax is somewhat confusing, but I guess it maybe depends on your perspective. Okay, so let's have a look and try that out. A equals reshape. Okay, so that gives us what we were aiming for. Now I'm going to try to get fancy, okay? So I'm not always good at trying new things, but let's just do that. So up here, I remember I can go insert, cell above. Insert cell above. So let's try this. Okay, great. Now I've got a new cell. So let's take a piece of this out because I had a question earlier. So if I just take this, collect 1 and 21, are we actually getting the numbers from 1 to 21, or are we getting something else? Okay, so that's running. All right, now I see that we have a column vector from 1 to 21. Okay, so that answers that question. And then the reshaping of it is what would be partition in Mathematica, so breaking this up into triples, except here you've got a 3 and a 7. So anyway, okay, so now I think we understand that. So let's move on. Now rank. So we're entering into memory. So have I done this? I think I have. So yeah, so I think I'm up to that. I've got the matrix A in memory. Now rank, this is the dimension of the row space of the matrix A. But there's a nice result that says that the dimension of the row space of a matrix is equal to the dimension of the column space of a matrix. And we call that the rank, okay? So in other words, you can use row reduction, Gauss-Jordan reduction, to calculate the row reduced echelon form of the matrix. And then you can look at that to find out what is the dimension of the linear space consisting of the rows, or the row space. Okay, and I'll just skip ahead here and talk about this because putting in row reduced echelon form, or RREF, into Julia, we get the row reduced echelon form, and what we see is we have 2 pivots right here where this one has zeros below it, and then there's another pivot here. This one has zeros below it, zeros above it, and zeros to the left of it. So those are 2 pivots. So these two rows, the first 2 rows from top down, they span as vectors the row space of this matrix. But also, since the row space is equal to the column space, we know that the column space has dimension 2. And in fact, the column space, so I'm trying to highlight that, but that's not working. So the first 2 columns are vectors that span all of the columns of this matrix. So in other words, all of the other columns should be linear combinations of the other two columns, the leftmost two columns. And you can see that straight away. It's obvious, right? Because, for example, the vector consisting of entries -1, 2, 0, as in the third column here, that's a linear combination of the first two vectors, in first two column vectors there, because it would be -1 times the first one plus 2 times the second one. All right, and that's a linear combination. Likewise, you can obtain all of the other columns in that way. Okay, so below we're going to see exercises on how you actually find those numbers using Julia. But let's go up here and run this stuff. So rank, you can see it's going to be 1. So yes, that works, great. Okay, next we've got to put in using row echelon. I can see I get an error here straight away. Okay, so this is not enough here. So we need something else. So I'm going to go up here and insert a cell above there, and I'm going to have a peek at my cheat sheet over here, the PDF, because I did this at home, and this is the first time I'm actually running this Jupyter script here on this laptop, right? So I've used my own PC at home to try this out together with Mathematica so that I understand this. So let's have a look at what I meant to enter on the computer beforehand to get this package to work. Okay, so my notes tell me that I need to write import. So let's try to shift this over a little bit so I can see it. So import, import, and then uppercase PKG, semicolon, and I probably need a space, I'll put one. Okay, uppercase PKG dot add, and then round brackets, and then what do I need to put inside? It's probably row echelon, but I'll have a look. Yep, row echelon with an uppercase E. And remind me if I don't spell that correctly. Okay, row echelon. Does that look right? No, it's red color, which kind of worries me, but let's try it out. Shift and enter, and I can see it's running now, which is a good sign. Taking a little while. Okay, great. Now, some of you were having some problems last week in loading some plots. So you might just take note of what I've put in here, right? Because sometimes being not totally familiar with all of the things that you have to load here in Julia, sometimes we put using, and this time I've put import, right? So I don't know a lot about that. I've just done some trial and error here. Okay, so it seems to still be running. Okay, I bet if I just look at my PDF, I would have, oh yeah, using row echelon. Okay, great. Thank you, Walla. All right, so I'll go up and insert another cell. So using row echelon. Okay, shift and enter. And that's running. Seems to have gone through. So now I'm tempted to go and make a new line and put row reduced echelon form, but I want to know a question. Is it going to care about the order? So I'll go up here and try it again. Okay, great. It doesn't care about the order. That's good to know. Okay, great. So that runs. Now, like I was saying earlier, what we're going to do is we're going to work out that the third column is a linear combination of the first two, and we're going to get those coefficients. But they're obviously -1 and 2, right? Now, so how we do that is we use indexing. So this is another chance for you to practice your skills at indexing, or at least remember what you're meant to do. Okay, so we have x3 equals uppercase A, left square bracket, colon, and then we have comma 1, colon 2. So what that is basically all of the entries. So in other words, every element of the rows as we go through columns 1 to 2. All right, now in Mathematica, I would put an all there rather than the colon. All right, but this gives us precisely that. This gives us columns. Columns 1 to 2. Okay, and then here we have a backslash. So what we're doing is we're solving a matrix vector equation where you might imagine an invisible vector z, so that what we have is this. The left part, the first two columns times the vector z equals this third column, which is another vector, right? So we're solving that system. Okay, so let's try this. And great, that works, and it's precisely as expected. We get -1 and 2 in our vector z, but what that's giving us is the coefficients, right? What we would multiply together to realize that as a linear combination of the first two columns. Okay, now down below we've got a lot of the same, so I'll just skip that. But I have to stop somewhere where we're seeing something new. Okay, rank A, well that's still going to be 2, I believe. All right, so let's go to this point. V equals -1s, 3. And you can see down below what the output is, so it's not hard to guess what the syntax is doing. It's just giving us a vector of the negatives of -1, but 3 rows of this. Okay, so let's run that, because that puts that into memory. Now, norm. So the norm, if you just do this norm of V, that is the Euclidean norm. So this should be the square root of this sum of the squares. So in other words, the square root of 1 plus 1 plus 1 plus 1. So the square root of 3 and 1.732. So this is one of the things that I thought would be a good idea to memorize when I was a kid. Okay, so that's the Euclidean norm, and you can see that this matches the square root of 3. All right, now next, norm V comma 1. So what is this? Well, this is the L1 norm, which is the sum of the absolute values of the entries. Okay, so we can see, since we have -1, -1, -1, the sum of the absolute values would be 1 plus 1 plus 1, which is 3. Okay, so that's a different kind of norm, which is useful for some other things. Okay, now also we have the infinite norm. All right, so if you were writing this, you would write, you would put V, and then on either side you would put 2 vertical lines. All right, so 2 vertical lines, and then you put the subscript infinity at the bottom right of that. Okay, but this is, and I'll just run it. This is the maximum absolute value of the entries. Okay, and we got 1. All right, so let's just try this again on the vector 1, 2, -8, 3. Okay, and we get 8 just as expected. All right, now normalize. So what we're doing here is we're forming a unit vector. So this is simply to divide by the norm of the vector, which produces a unit vector, but there's a nice command called normalize that does that for us. Okay, and there it is. And now let's check, because we've put this in the memory now. V is the normalized of the earlier V, and we'll just check that the norm of this is actually 1. Okay, and that looks good. Now, I'm going to have a look at the Mathematica PDF that I've got over here, because it gives us some notes on this. So I'll draw your eye to the biggest thing here, right? So this matrix here, this is called a van der Mond matrix. So van der Mond right there with a big V. And what we're doing here is we're using this to get a formula that matches some data. So if you have some points and you suspect that that should fit some nice polynomial, then you might want to do interpolation to find a polynomial that best fits that, okay? But this exercise will show that it's not always great at fitting a sensible polynomial to the data. Sometimes least squares is, well, much better at doing it. So this will give us roughly, up to truncation errors, it'll give us an exact fit. Okay, now, I noticed straight away that this, okay, so first of all, I'll properly introduce this. So have a look at the matrix, okay, that I've displayed as a matrix here. So what I have is a 4x4 matrix, and it has x0, x0 squared, x0 cubed, and so on, right? So the entries are predictable in this Vandermonde matrix. And then we go down in the next row and we've got x1, x1 squared, and so on, right? So the rows increase in the subscript, the columns, the entries in the columns increase in the power, and that's an actual power, not another subscript or superscript. It's a power. All right, so this is multiplied by the coefficients of the polynomial that we're seeking. Okay, so if we have 4 data points, say P1, P2, P3, P4, and they have coordinates, well, actually, I should have said P0, P1, P2, P3, right? Because I've got subscripts 0 to 3. Okay, so if P0 is x0, comma y0, and so on, you get the pattern, right? Then basically, I want to form this matrix, and where I put all the y values on the right-hand side, and then I want to solve the matrix system for the coefficients C0, C1, C2, C3, and those will be, you know, coefficients of the polynomial just like this. So this is Mathematica code here, incidentally, and this was suitable because this is a symbolic calculation. Okay, so the coefficients are here, and I've used indexing to provide those. Okay, so this is C0, C1, C2, C3 there times these x to the power of something. Okay, so we should get a polynomial in the end as we solve that, right? So, but some of you may be familiar with the Lagrange polynomial. So I could see that if you did solve this, what you should get is this Lagrange formula, right? Now I got 2 hints. I got a hint from looking at the result and what the shape of the polynomial is. And it does a similar sort of thing to Lagrange interpolation in that you can fit rather exactly to some data, but it may not be a best fit in terms of something like least squares, right? So this is what the Lagrange formula looks like. Now you have a sum from 0 to n of the y parts of the data, and then you've got products, right? So I've separated 2 products there because I wanted to run this in the computer. But the way you write this formula symbolically is you just say avoid the case when I is equal to j, all right? And that looks prettier, but it's not. You want to be able to run this on a computer, right? Which I can do. So this is Lagrange. And it turns out that these 2 things are the same. So running this sum, this Lagrange sum, gives you the same result as solving this linear system here from the Vandermonde matrix interpolation. And that's not obvious until you do a symbolic calculation. So I've entered these symbolically. And then all of this here is me checking that this polynomial here that I get from Vandermonde is the same as this sum formula that I get from Lagrange. So basically you see that I've entered this Mathematica there, LG equals this, and it's inside expand. So I've expanded, collected that. And then, so there's some superfluous calculations symbolically in here, but then I've expanded the difference, L minus V. So this one minus this polynomial, and then factored it. And then after all that, I could see that I get 0. So those are equal, right? But you get a hint here in that this relates to discriminants in number theory. Okay, and being a number theorist, I have some familiarity with that. So the determinant of this relates to the discriminant. And that looked a lot like what we see in the denominator here. So I had a hunch that solving this system would give the Lagrange polynomial. And it turns out that it does, at least for degree 3, but I'm pretty confident that it should in higher degrees too. But I didn't get around to writing up a proof. Anyway. All right, so back to Julia. We want to be able to do this in Julia. Now keep in mind that Julia doesn't do symbolic calculations. Okay, so let's just have a look at the output here, right? So you get an idea now. Okay, so we've got a few different colors here, right? So the big black things are data, all right? Some data points that you got from who knows where. And let's suppose that you wanted to find a fit. Now, obviously, the best thing to do here would be to fit this data using least squares because it seems to be a nice, well, it should have a nice linear fit, and that would be the most sensible thing to do because all of them are pretty close, well, to zero relatively, okay? So a horizontal line seems to be a reasonable fit there. Whereas you can see this Lagrange polynomial, which is degree 5, well, that's a rather, it does fit perfectly, you see, right? But it's a rather silly thing to use as a predictor for what this data would be doing, okay? So that's the pitfall of using the Lagrange interpolation formula, in that you might be able to get an exact fit, but if whatever you're dealing with shouldn't be predicted by a degree 5 polynomial, then that would be a bad idea. But this makes a nice exercise here to do this computationally. Okay, so let's just have a browse at the code here, right? So what we're doing here, the first line would be to enter some x values. The second line, the y values, okay? So the x0, x1, x2, and so on. How many have we got here? It looks like we've got 6 of each, so 6 points. If you're thinking in terms of two tuples, you'd match the x coordinate and the y coordinate, and you'd have 6 points. Now let's scroll down. Yep, I see 6 points, so great. Okay, and then n would take the length of that. Well, you only need the length of one of them. Okay, now the next line is to form that Vandermonde matrix. Okay, so what you're doing is you're just taking the x values, you're doing indexing here. You've got an I plus 1 inside the bracket because we want to be able to start from 0 and go up to n minus 1. Okay, but when you're indexing, you don't want to say, I pull out the 0th entry of the vector, right? Because it's not, that's what Python would do, if I remember that right. I don't know about the latest version of Python. It's been a while since I used Python. But Python likes to start with 0, whereas some other software, Julia included, would like to start with 1 as the first one. Okay, so that's why we need an I plus 1 there. So this is just forming the Vandermonde matrix. Now the next line here is just solving that, and we can see C equals, but that's C a vector, right? Whose entries are the coefficients. And then we form a grid, -5 to 20. And then this would give us the polynomial that we're then plotting, okay? So that's the basic idea there. Or maybe I needed to get rid of pyplot to make that work. I'll try it anyway. Okay, that's going to take a while, but while we're waiting for that, let's go have a look at the next line. Okay, so P inverse. Now, I don't know what that syntax means, but if I speculate here, because I know that in the plot, we have a beta 0 and a beta 1. Now, I understand that that would be finding a least squares fit of the data, which would be a better fit than, or a more appropriate fit than the polynomial. Okay, so this one here is giving us a least squares solution to that. So beta 0 and beta 1 would be coefficients of a line of best fit, right? And in a line, you know, it's only got degree 1, so we should only have a beta 0 and a beta 1, where I would guess that the beta 1 is the slope. Okay, but there's a P, I, and V. Now, I'm only speculating because I happen to know what this calculation is about, but I speculate that this is a pseudo-inverse, okay? Now, a pseudo-inverse, you could think of it as a generalization of a matrix inverse. So it should give you the actual inverse if you have a square matrix that is invertible, okay? But it works also to calculate a pseudo-inverse of something like a 2 by 3 matrix. Now, what it also does is it allows you to do a least squares fit, okay? Because when you have the pseudo inverse times your y values, it's kind of like taking A inverse times the vector b, and you would get, you know, the answer to ax equals b. But when, well, in general, it gives you a best fit. So, and that is least squares. Okay, so this I'm speculating that this is pseudo inverse PINV. Okay, so let's scroll up. I think this is run now, and so you can see it gave us the same thing as before. But let's try and run this and see if it goes through. I don't know that I did this one at home, but I'll run that with you and see if we get. Yep, it works perfectly. Okay, now the rest of this sheet, and I can see we're out of time and I want to run out and get a drink of water. The rest of this sheet deals with random matrices. It's a really nice exercise, so you should do that. But I'll just describe what's going on here. And actually, I could probably most efficiently do that with my PDF here. So I might just talk about Mathematica for a little bit. You can see the pretty nice Mathematica plots of the same. Okay, so in the next exercise, what we're doing basically is we're forming a random 3x3 matrix with entries belonging to the collection 1, 2, 3. Right, now here's some Mathematica code for doing that, where the 3x3 is in the second part. And then in the task, you're then building a function to do that. So this here is Mathematica code, but in Julia, this is the simple code for doing that, right? So we just build a function, rm round bracket with nothing in it, equals rand. Now that's a built-in function. And then the first input is 1, 2, 3. So this is a vector. So this is where we're drawing from. And then it's saying 3x3. So you can see that's the syntax to do that. Okay, and then the next part of it is to do 10 to the 5th of these such random matrices where you're drawing from 1, 2, 3, and then to form, well, to count how many of each one you've got. Okay, so I'm describing Mathematica code here, but the Julia code is very similar, right? So basically, doing 10 to the 5th of these gives us a count of how many of each rank. Okay, so now we've got 79,842 of rank 3. So that's 79,842 invertible matrices from that collection. Okay, now every time you do this, it should be slightly different. But if you look at the proportion, here I have 79%, or roughly 80% of those matrices are invertible when you do that. Okay, and how we measured that was that they had rank 3. Okay, so that's all, guys.